A traditional single-core processor eventually hits a hard physical limit. You can only shrink silicon transistors so much, and you can only push clock speeds so high before heat and physics prevent the machine from running any faster. Because a traditional processor executes exactly one instruction per clock cycle in a strict sequence, it creates a rigid ceiling. When software requires millions of calculations per second to render complex graphics or train models, sequential execution simply cannot scale to meet the demand. To bypass this physical bottleneck, computer architects developed two distinct engineering pathways: pack more computing resources tightly together onto the silicon itself, or connect separate independent machines across a wide network. Parallel processing takes the first path. It is a tightly coupled approach that groups multiple processors together within a single physical machine. It optimizes for absolute execution speed, chewing through a single complex task as fast as possible. Distributed systems take the second path. This is a loosely coupled approach. Instead of sharing a single motherboard, it relies on entirely autonomous networked nodes. This sacrifices raw internal speed, but optimizes for infinite horizontal scalability. Both of these paradigms exist to solve the same problem, scale, but they achieve it by organizing the relationships between hardware, instructions, and data in completely different ways. To understand modern computing architecture, from the multi-core chip inside your laptop to the global server clusters powering the cloud, we have to trace exactly how these systems manage the flow of those instructions and data streams. We start at the bedrock of computation, SISD. SISD, Single Instruction Stream, Single Data Stream, is an architecture where a single processor executes one instruction at a time on one data piece. In an SISD system, a single control unit utilizes a program counter to enforce strict serial execution. It fetches one instruction, processes one piece of data, and moves to the next, entirely in order. This schematic illustrates pushing past the sequential bottleneck by introducing parallelism into the execution unit. Instead of one monolithic processor, the hardware divides into specialized blocks, like an adder-subtractor, logic unit, and floating point multiplier, routing different operations to different circuits simultaneously. Because these units are independent, one number can be shifted in the logic unit, while a completely different number is multiplied in the floating point unit at the exact same time. However, this specific approach has a ceiling. Even with multiple functional units firing concurrently, the processor is still restricted, fed by a single overarching instruction stream from the control unit. To move beyond the throughput limits of a single instruction stream, architects began implementing multiple streams. To make sense of these different configurations, we use a framework called Flynn's taxonomy. Flynn's taxonomy is a classification system used to categorize computer architectures by how they handle instruction and data streams. It maps whether a system processes single or multiple instruction streams and single or multiple data streams. This diagram shows SIMD, single instruction, multiple data. One control unit broadcasts the same instruction to multiple processing elements. It excels at vector processing, where every processor executes the identical command simultaneously but on different pieces of data. This hardware limitation introduces an architectural paradox. What happens when the software code requires an if-then branching decision, but the hardware forces every processor to execute the exact same instruction? This flowchart demonstrates the solution. To handle divergent software branches, a SIMD system converts conditional operations into a sequential mask. Processors not satisfying the condition simply mask out and remain idle, waiting for active processors to finish. SIMD provides massive speedups for uniform, predictable tasks like rendering pixels on a screen. But because of this rigid, synchronous execution model, it is inefficient for handling complex software logic with heavy branching. For complex logic, we rely on the modern standard for general-purpose computing, MIMD. MIMD, or Multiple Instruction, Multiple Data, is an architecture where multiple processors execute different instruction streams using different datasets simultaneously. MIMD multiprocessors feature fully independent cores. Each core can execute entirely different programs on entirely different data streams simultaneously. But adding independent processors creates a new hardware bottleneck. To work together on a system level, all these independent processors must synchronize and communicate by reading and writing to physical memory. In a UMA, or Uniform Memory Access model, all processors share centralized physical memory via a single bus. When too many CPUs hit that single narrow memory bus simultaneously, it creates a significant hardware bottleneck. This model illustrates NUMA, or Non-Uniform Memory Access, designed to scale beyond UMA limits. Shared memory is physically distributed into local blocks paired with individual processors. To access remote data, a CPU must cross an interconnection network. For a software engineer, this distinction dictates performance. Accessing a local memory block is incredibly fast. Retrieving data from a remote memory block introduces severe latency that slows down execution. NUMA successfully pushes physical, shared memory hardware to its absolute limit. In order to scale computational power any further, the architecture must physically break the boundaries of a single machine. This diagram maps the transition that occurs when a physical machine simply cannot hold any more processors or memory: distributed systems. A distributed system is a collection of completely independent nodes. Each computer in the network operates with its own independent local memory, hardware resources, and operating system. Looking at this schematic, you can see that unlike NUMA, these nodes do not share a physical memory bus. To communicate, they must assemble data into discrete modules and pass messages back and forth over a network. Because these systems are isolated, they require a crucial software interface called middleware. Middleware is software that acts as an interface between separate computers to coordinate activities and share resources like data and hardware. This architecture requires a specific trade-off. We sacrifice the raw, synchronous execution speed of an internal CPU memory bus. In exchange, we gain immense fault tolerance. If a single hardware node fails entirely, the tasks are rerouted, and the overarching system survives. By utilizing this network of autonomous computers, a distributed system maintains a powerful illusion. To the end user, it appears and functions as a single, coherent application. Ultimately, scaling computation comes down to a choice between two distinct architectures: the tightly coupled parallel machine and the loosely coupled distributed network. Parallel computing optimizes for raw speed, using tightly coupled processors to execute a massive task instantly. Distributed computing instead uses microservices, autonomous services modeled around business functions. This adds latency, but scales horizontally, spinning up virtual servers for high volumes of requests. The engineering challenges for each are distinct. Tightly coupled parallel systems fight a constant war against shared memory traffic. Loosely coupled distributed systems battle network latency and node synchronization. These are not competing technologies. They are complementary layers that form the backbone of the modern cloud stack. Modern software engineering requires a mastery of both domains. You must write parallelized, memory-efficient code to maximize the physics of the local processor and deploy that code across a resilient, loosely coupled network to serve the globe.